Good morning, one and all. So today we will be discussing about the derivation of efficiency of the Brayton cycle. Now, listen here. What we are supposed to do is, whenever I say take it down, then you have to take it down whatever I say. Whenever I say listen here, you have to just listen. You are not supposed to take down what I say. Is that clear? So now we'll be starting this. Take it down. Derive an expression for thermal efficiency of a Brayton cycle, okay? Or it might be asked as derive an expression for thermal efficiency of Brayton cycle in terms of temperature ratio as well as the pressure ratio, okay? So this is the question. Now listen here. The Brayton cycle, as you all know, it consists of the four processes: 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So before you start any derivation of any cycle, you have to draw the PV diagram as well as the TS diagram along with the different types of processes involved in it, right? So the PV diagram of the Brayton cycle is as such: 1 to 2 is adiabatic compression, 2 to 3 is isobaric heat addition. That means the heat addition takes place during the process 2 to 3. And 3 to 4 is adiabatic expansion, where the work is extracted. And the 4 to 1 is isobaric heat rejection, where the heat is outputted from the system. So just list out the table as you have done in the previous class. Just process 1 to 2, 2 to 3, 3 to 4 and 4 to 1, and what are the types of the processes. It is enough to write what is the heat input. So generally we are adding heat in 2 to 3, right? So 2 to 3 is isobaric heat addition, so it is mCp T3 minus T2. Similarly, 4 to 1, where the heat is being rejected, that is Q4 to 1 is heat output, where it is given as isobaric heat rejection, right? So it is mCp delta T. So mCp final minus initial T1 minus T4. Just note down the heat flows of these two processes is enough for this particular thing. Now, as you all know, efficiency of any cycle is given by net work output divided by the heat input. So net work output is equals to the net heat flow of the cycle because of the first law. What does the first law say? The net work flow is equal to net heat flow, right? So net work flow is equal to net heat flow divided by heat input is what? Heat input is nothing but Q 2 to 3. After that, total heat interaction. So it's the summation of heat input and heat output. So it is Q2 to 3 plus Q4 to 1 divided by Q2 to 3 as it is. Just substitute the values whatever it is. Q2 to 3 is mCp T3 minus T2 and Q4 to 1 is mCp T1 minus T4. Similarly, Q2 to 3 is mCp T3 minus T2. So mCp you can just take it common and cancel it. So T3 minus T2 divided by T3 minus T2 is 1 plus T1 minus 4 divided by T3 minus T2 is as such. Now what you are doing is you are replacing the numerators to change the sign. So efficiency of Brayton cycle is given by 1 minus T4 minus T1 divided by T3 minus T2. So just take it down from here, completing here up to the equation 1. Okay. So continuing further, we have taken equation 1 as efficiency of Brayton cycle is equals to 1 minus T4 minus T1 divided by T3 minus T2. Now what we will be doing is we will be applying the PVT conversion equations for the processes 1 to 2. So for the process 1 to 2, which is adiabatic in nature, the PVT conversion equation is given as P1 by P2 is equals to V2 by V1 whole to the power of gamma, that is equal to T1 by T2 whole to the power of gamma divided by gamma minus 1. So in this particular equation A, we will be defining two important parameters. Number one is the pressure ratio, which is indicated by beta. So as in case of a dual and diesel cycle, here also the pressure ratio is nothing but P2 by P1 or P3 by P4. Okay. Similarly, the second main parameter we are defining is the temperature ratio. We are indicating this particular thing what T to the suffix R. T to the suffix R, that is equal to, same as, no need to confuse here, P2 by P1, here it is P2 by T1. Here it is P3 by P4, the temperature ratio is T3 by T4. So no need to confuse here. So it is T2 by T1 is equals to T3 by T4. That is given as the temperature ratio. So what are the two important parameters we are defining at the start? Number one is the pressure ratio, which is indicated by beta. Number two is the temperature ratio, which is indicated by TR. Continuing further, T2 by T1 is equals to T3 by T4. I have taken it here. I just shuffled the terms where T3 by T2 is equals to T4 by T1, which will be helpful in the further part of the derivation. We shall look at it. Now, once you have defined the pressure ratio and the temperature ratio, substitute the same in equation A, which is PVT conversion equation. So substituting the pressure ratio and temperature ratio in equation A, I have taken it here. So P2 by P1 is the beta. So P1 by P2 is 1 by beta. Similarly, T1 by T2 is what? 1 by TR, because TR is T2 by T1. So now, 1 by beta is equals to 1 divided by TR whole to the power of gamma divided by gamma minus 1. So shuffling the things up, beta is equals to TR whole to the power of gamma divided by gamma minus 1, which I am taking it as equation number 2. So you have obtained the equation number 1, which is efficiency in terms of different temperatures, and equation number 2, which is the relation between beta and TR, and you have also obtained this relation using the temperature ratio, that is T3 by T2 is equals to T4 by T1. We shall continue further. So taking this efficiency equation, which is equation number 1 minus T4 minus T1 divided by T3 minus T2, what I am doing is, in the denominator, I will take T2 as common. If I take T2 as common, there is nothing here, so I have to divide it by T2. If I take T2 common, 1. So it will be T2 into T3 divided by T2 minus 1. Okay, after that, we have stated a relation using a temperature ratio, that is T3 by T2 is equals to T4 by T1, right? So what you will be doing is, you will be replacing this particular T3 by T2 as T4 by T1. So once you are replacing it, take LCM here. So T1 in the numerator, it will be T4 minus T1. Similarly, it comes here. So once you take the LCM here, T4 minus T1 divided by T1. See, if you closely observe, T4 minus T1 and T4 minus T1 will be get cancelled, which is in the numerator and the denominator, right? So this particular term and this particular term will be get cancelled. So you'll be left out with 1 minus T2 by T1. Clear? So what is T2 by T1? Again, it is a TR. So 1 minus 1 divided by TR. So again, from equation 2, you have the relationship between the beta and the TR, right? So beta is equals to TR whole to the power of gamma divided by gamma minus 1. So I want TR here. So TR is equals to beta whole to the power of, if you transfer this particular thing, gamma divided by gamma minus 1 to the either side, what happens? It becomes a reciprocal of it. So it will be gamma minus 1 by gamma. So TR would be equal to beta whole to the power of gamma minus 1 by gamma. So replacing TR with beta whole to the power of gamma divided by gamma minus 1, you will get the final expression for the thermal efficiency of a ideal Brayton cycle. Listen, this is very, very important, and it has been asked many times in your previous exam question papers. Okay.